Hello guys, and welcome to another calculus video. In this video we are going to be solving this awesome integral right here, which was posted in my Discord by a viewer of mine. It's a really wild ride and we use a lot of different tricks in it, so I'm really excited to show you guys this integral. One thing that you guys should probably note before you watch is that we will not have a closed form solution. It will be in the form of a summation, but it is a pretty cool looking summation if you want to stick around to find out. So without any further ado, let's go ahead and jump right into it. So this is the integral from 0 to 1 of Li of x over x squared times e to the x times x minus 1 plus 1 dx. And in this case, Li of x actually represents the logarithmic integral function, which is just the integral from 0 to x of 1 over ln t dt. Now the direct result of this is that the derivative of Li of x is 1 over ln x, which immediately suggests that we should be trying to use integration by parts, because we want to reduce this from an integral function into a normal type of function. So what we notice then is that we have to take everything that isn't Li of x, and we're going to have to integrate that if we want to differentiate Li of x using integration by parts. So taking a look at this is going to end up giving us e to the x over x minus e to the x over x squared plus 1 over x squared. And this is definitely the little trick that is going to let us, make a lot of progress on this integral, is that this is actually the derivative of e to the x over x minus 1 over x. So we can rewrite this integral as the integral from 0 to 1 of Li of x d e to the x over x minus 1 over x, which is the same thing as Li of x times e to the x over x minus 1 over x evaluated at 1 and at 0, minus the integral from 0 to 1 of e to the x minus 1 over x ln x, which is all very nice. However, this actually does not work. And why, you may ask? Well, the reason for this is if we take the limit as x goes to 1 of this function right here, Li of x times e to the x over x minus 1 over x, it actually goes to infinity. So that means we can't evaluate this first part of the integral. And also, since we know that this is going to go to infinity, we know that this will also go to infinity because the original integral was finite. So this is a pretty serious problem. How are we going to deal with this? Well, actually, this is a really useful trick that I have used in a lot of different types of integrals to make them a lot easier and simpler to evaluate. Sometimes it can even eliminate entire steps from the integration. When we're using integration by parts, we have u dv, right? Then we integrate that and we get uv minus v du. So in this case, what this actually means is the important part here is when we integrate this first term, when we integrate dv, the integral of dv, which in this case v is just e to the x over x minus 1 over x, we actually get e to the x over x minus 1 over x plus c. So we can actually choose this constant c to be whatever we want, and usually we just don't really worry about it, and we just, choose c to be whatever it is that makes our integrated function look very nice. However, in this case, we actually want to choose a different c, because now, if we choose a different value of c, we know that Li of x is going to infinity as x goes to 1. But if we can make this part of the integral go to 0, then we'd have a 0 times infinity in determinate form, and we could take a limit and hopefully get something that is finite, obviously, right? So we want to choose c so that when x is 1, when x goes to 1, this goes to 0. So in this case, if we plug in e to the 1 over 1 minus 1, it's just going to give us e minus 1. So our c should be 1 minus e, because then this entire function evaluated x equals 1 is just 0. So this is what that's going to look like. So we have integral from 0 to 1 of Li of x d e to the x over x minus 1 over x equals Li of x times e to the x minus 1 over x plus 1 minus e evaluated at 1 and 0 minus the integral of v du. So as x goes to 1 from the bottom, Li of x is approached by acts similarly to ln 1 minus x. And the reason for this is that natural log of x around x equals 1 acts like acts like x minus 1. So we're integrating 1 over x minus 1. It's going to essentially give us ln 1 minus x, right? And then e to the x over x plus 1 over e. If you go ahead and write e to the x as a power series, you'll find that this is approximates 1 minus x as x goes to 1. or you could just do L'Hospital's rule and figure out that these have the same limit. And so we end up with the limit as x goes to 1 minus of ln 1 minus x times 1 minus x to give us the order of our solution here, and it ends up going to 0, which means that this upper bound just goes to 0 as well. Then as x goes to 0, Li of x goes to 0, and this goes to a constant 2 minus e. So that means overall Li of x times this is just going to go to 0 as well. So both of these bounds just completely disappear with our new choice of adding 1 minus e. So overall, our integral I is just going to end up being negative the integral from 0 to 1, e to the x minus 1 over x plus 1 minus e, all over ln x dx. Now, this ln x on the bottom is not fun to deal with, so we're just going to go ahead and substitute x equals e to the negative u, which means that dx is going to be negative e to the negative u du. After we simplify everything, we get the integral from 0 to infinity of e to the u minus 1, e to the u minus 1 plus 1 minus e times e to the negative u, all over u du. So we see a lot of e to the negative u stuff, and we're also over u right here. So this looks like a perfect place to go ahead and try using the Laplace transform. So we'll define our function f of x as this function on top, and we'll calculate the Laplace transform of f of x. And after we calculate the Laplace transform of f of x, we can calculate the Laplace transform of f of x over x using the rules for the Laplace transform, which will give us the Laplace transform of this function. Then we can just plug in s equals 0, and that'll give us the integral of that function from 0 to infinity. So, the Laplace transform of f of x, for this minus 1, it's just going to give us minus 1 over s. And for this term right here, it's just going to give us this term right here. This term over here is where we're going to have a little bit of trouble. So the way we're going to do this, I wrote e to the negative x, let's just say t right here, since I was writing it in terms of t, but it doesn't really matter. So we're going to actually expand e to the negative x as a power series in e to the negative x. So we're going to get the sum from n equals 0 to infinity of 1 over n factorial times the integral from 0 to infinity of e to the negative s plus 1 times t dt minus those other terms. And so we're going to end up with the sum from n equals 0 to infinity of 1 over n factorial times s plus n, that's in the denominator. However, what I'm actually going to do is I'm going to write this as the sum from n equals 2 to infinity, and then I'm going to take out those first two terms. So the first term, plugging in n equals 0, we're just going to get 1 over s, and that actually cancels with this 1 over s that we had over here. And for the second term, we're going to get 1 over s plus 1, which actually is a like term that we'll combine with this over here. So that way, we're going to end up with the Laplace transform of f of x equals 2 minus e over s plus 1, plus the sum from n equals 2 to infinity of 1 over n factorial times s plus 1 in the denominator, and we'll just call this f of s. Now remember that Laplace transform of f of x equals the integral from s to infinity of this should say f of u du, or f of s ds works fine. It's just a little bit confusing to have f in both places. So just imagine this says f of u du. So this means that our integral I is going to be the integral from 0 to infinity of f of x over x dx, which is the same as the Laplace transform of f of x over x evaluated at s equals 0. So we can just go ahead and plug in s equals 0 right here, and we're going to get the integral from 0 to infinity of 2 minus e over s plus 1, plus the sum from n equals 2 to infinity of 1 over n factorial times s plus n. So anyway, the actual integration here is not too difficult since we just have 1 over s plus n, right? So we end up with 2 minus e times natural log of s plus 1, plus the sum from n equals 2 to infinity of 1 over n factorial, natural log of n plus s, evaluated at infinity and at 0. So to aid us in evaluating this limit right here, we're going to use the fact that the sum from n equals 2 to infinity of 1 over n factorial is the same as the sum from n equals 0 to infinity of 1 over n factorial minus the first two terms, which are both 1. So that means this is right here is e, and this is just minus 2. So overall we get e minus 2. So we can actually write this as negative the sum from n equals 2 to infinity, and we can combine both of these summations into one summation. So we get the limit of as s goes to infinity of the sum from n equals 2 to infinity of natural log n plus s minus ln s plus 1 over n factorial. Minus, when we evaluate at 0, this term just disappears since we have natural log s plus 1, and we just end up with this term. So minus natural log n equals 2 to infinity, natural log of n over n factorial, just plugging in s equals 0. So for this limit right here, we'll bring it over here, and then, so our answer, I, is going to be negative sum from n equals 2 to infinity of this natural log over n factorial, plus the sum from n equals 2 to infinity of 1 over n factorial times this limit right here, But notice, if we combine these natural logarithms, s is going to dominate since s is going to infinity, so we can just say that this is going to be 0, and we're overall left with our final answer, which is this very, very nasty looking, but ultimately very cool summation for I equals negative the sum from n equals 2 to infinity of natural log of n over n factorial. Thank you guys so much for watching the video. I hope you enjoyed. If you have any suggestions for problems, you can leave them in the comments on YouTube, or you can go ahead and put it in problem post in my Discord server, which you can feel free to join. Anyway, hope you guys enjoyed the video, and I'll see you next time. Thanks. Bye.